Shine a laser at a polished gold surface. Almost everything bounces back. But hidden in that surface, invisible to your eyes, invisible to any standard microscope, there's a wave that could be running along it, hugging the metal the way ripples skim a pond. The catch? Your light can't reach it, not directly. There's a mismatch, and bridging that mismatch is the foundation of nearly every modern nanophotonic device.
In this video, we'll start from one simple question: what is the momentum of a wave? And walk all the way up to a technique called SNOM that lets you actually see these hidden waves on your own material. By the end, you'll have a practical playbook, not just the theory.
Forget photons for a second. Think of a wave on water. It has a wavelength, the distance from crest to crest, and it travels in a direction. If you compress that wavelength, the wave packs more oscillations into the same space. Physicists capture that with a single number, the wave vector, k, equal to 2 pi divided by the wavelength. Here's the leap. K is a kind of momentum. A short wavelength means a large k, which means a large momentum. Light has it, sound has it, and as we'll see, surface waves have it too. Theirs is bigger. For visible light at 633 nanometers, a standard red laser, K is about 10 million inverse meters. Keep that number in your back pocket.
Now meet the surface plasmon polariton, the SPP. It's not light alone. It's not electrons alone. It's a hybrid, an electromagnetic wave locked together with the collective sloshing of electrons just inside a metal. It rides the boundary between metal and air, like a swell trapped between two layers of ocean. Because it's bound to the surface, it doesn't follow the same rules as free space light. Its dispersion relation, the formula that links its frequency to its wave vector, is set by the metal and the dielectric it touches. KSPP equals K naught times the square root of epsilon metal times epsilon dielectric divided by their sum. For gold facing air at red wavelengths, that works out to a wave vector roughly 4 or 5% larger than free space light. Sounds small. It isn't. That few percent is the entire problem. Here's the rule. When two waves want to couple, when energy wants to flow from one into the other, their wave vectors along the surface must match. Conservation of momentum, no exceptions. But KSPP is bigger than K naught. So when you shine a laser at a flat gold film, the light's in-plane wave vector is too small. There's no overlap. The SPP exists, but the light can't get into it. It's like trying to push a child on a swing while running past. Your timing's wrong, so nothing happens. This is the momentum mismatch.
So how do we fix it? We give the light extra momentum along the surface, exactly enough to land on KSPP. There are 3 classic tricks. First, a prism. Inside a high-index glass, light carries a larger wave vector. Tilt it just right, the Kretschmann configuration, and the in-plane component matches the SPP. Energy tunnels through. Second, surface roughness. A randomly bumpy surface contains every spatial frequency you could want. Some of those frequencies match KSPP, and the SPP gets launched almost for free. This is why even an unstructured evaporated gold film can support plasmons. Third, and the one we'll focus on, a grating. A periodic structure with period capital lambda adds a discrete momentum kick of size capital G, equal to 2 pi divided by capital lambda. The momentum matching condition becomes K parallel plus m times capital G equals KSPP, where m is an integer, the diffraction order. The lattice supplies the missing momentum. The photon's frequency doesn't change. The lattice just gives it the extra k it needed.
You might wonder, if the lattice supplies m times capital G, can we crank m up to 100 and use any grating period we like? Mathematically, yes. Physically, almost never. Every periodic structure can be decomposed into its Fourier components, a sum of pure sine waves at the fundamental period, twice that, 3 times, and so on. The mth diffraction order is driven by the amplitude of the mth Fourier component of the grating profile. For a perfect sinusoidal grating, only m equals plus or minus 1 exists, nothing else. For a symmetric square wave grating, odd orders survive, but their amplitudes fall as 1 over m. By m equals 30, coupling strength is a small fraction of the first order. Even orders vanish entirely. Real fabricated gratings, rounded edges, finite resolution, sidewall roughness, lose their high-frequency Fourier components even faster. The practical consequence, nearly every plasmonic device on Earth runs at m equals plus or minus 1. But, and this matters, surface roughness has a broad Fourier spectrum. It doesn't pick a single diffraction order. It supplies a continuum of wave vectors. That's both a curse, it broadens and damps resonances, and a feature. It can enable couplings a perfect lattice would forbid.
Here's a confession the literature often skips. Many papers claim SPPs when the resonance they're seeing could be something else entirely. A periodic structure on top of a film can excite at least 9 different kinds of resonance, and they often produce eerily similar far-field spectra. A guided mode resonance lives in a dielectric slab. It looks like an SPP, but it works for both TE and TM polarization and shifts dramatically with film thickness. A Fabry-Perot cavity is 2 reflecting interfaces with a standing wave between them. Its resonance condition, twice the optical thickness equals m times the wavelength, depends on cavity thickness, not grading period. A localized plasmon resonance sits on an isolated nanoparticle. It doesn't need periodicity at all. Shuffle the array into a random pattern, and the resonance survives. A lattice resonance, sometimes called a surface lattice resonance, happens when a Rayleigh anomaly meets a localized plasmon. You get a hybrid mode with an enormous quality factor. A bound state in the continuum, a BIC, is a symmetry-protected mode that, in principle, should radiate but doesn't. Break the symmetry and it leaks out as a spectacularly sharp resonance. And LC resonance, the one you'd recognize from circuits, happens when a metasurface element acts like a tiny inductor and capacitor. Its frequency depends on geometry, not period. The point, a single reflectance dip is not enough to call something an SPP.
There's a beautiful experimental strategy here, and it needs no exotic equipment beyond what you already have: the parameter sweep. Vary one thing at a time: period, capital lambda, feature size, film thickness, angle of incidence, and track how the resonance moves. An SPP shifts strongly with both angle and period. A Fabry-Perot mode shifts with thickness and barely cares about angle or period. A localized plasmon ignores period and angle, but moves with particle size. A guided mode shifts with thickness. A Rayleigh anomaly is a pure geometry effect. Its position depends only on capital lambda and angle. That's your first line of defense. Build the table of how each candidate is expected to respond, then compare to what your sample actually does. Most of the time, the dominant mechanism falls out immediately. But sometimes it doesn't. Multiple mechanisms hybridize. Modes mimic each other in the far field. For those cases, the spectrum alone can't help you. You need to look at the near field.
A standard microscope can't help here. Visible light has a wavelength around 500 nanometers, and Abbe's diffraction limit puts a hard floor of roughly half that on what you can resolve. But the features that distinguish your resonance modes, hotspots, fringes, current loops, live at tens of nanometers. They are invisible by definition. Enter scattering type scanning near-field optical microscopy, SNOM. The trick is this: instead of imaging the far field, you bring a sharp metallic tip, typically AFM style, with a radius around 20 nanometers, within nanometers of the surface. The sample's optical near field, which never escapes more than a tiny distance from the material, couples to the tip. The tip scatters that near field into the far field, where a detector picks it up. You scan the tip across the surface, and you build a map of the optical near field with resolution set not by wavelength, but by tip size.
Now, the payoff. Each mode type leaves a different signature in the near-field image. A propagating SPP shows interference fringes, bright stripes spreading outward from edges or defects, where the launched SPP wave interferes with itself or with the incident illumination. Measure the fringe spacing, and you get lambda SPP directly. Be aware, the spacing can be lambda SPP or lambda SPP over 2, depending on whether the tip launches the SPP or merely observes a propagating one, a detail to confirm against your geometry. A localized plasmon shows isolated bright spots, confined to corners, gaps, particle tips. No propagation, no fringes. A Fabry-Perot mode shows a clean standing wave across the cavity, bright antinodes and dark nodes fixed in space. A guided mode shows fringes too, but the field is buried inside the dielectric film and decays into the air above it. An LC resonance shows a closed current loop,
an electric field maximum across the capacitive gap with magnetic energy circulating around the inductive arm. And if your SNOM measures amplitude and phase, most modern systems do, you gain something even more powerful. A traveling wave shows continuous phase progression along its direction of propagation. A standing wave alternates phase by pi at every node. A localized resonance has near constant phase across its hotspot.
Here's how you'd attack your own material. Say a periodic titanium nitride metasurface made by nanosphere lithography with periods of a few hundred nanometers. Step 1. Image the near-field amplitude. Look for the signature, localized hotspots versus extended fringes. This usually decides the gross character of the mode in a single scan. Step 2. Image the phase, if your instrument allows. That distinguishes traveling from standing from localized. Step 3. Take a 2D Fourier transform of the near-field image. Sharp peaks at well-defined wave vectors mean propagating modes. Broad spectra mean localized or disorder-driven resonances. Step 4. Repeat at several wavelengths. Track how the dominant near-field wave vector shifts. A propagating mode follows its dispersion. A geometric LC resonance sits stubbornly tied to your structure's dimensions. Step 5. Probe different locations. Edges, grain boundaries, periodic regions, defects. If a mode lights up only at edges, edges are supplying the momentum. If it lights up everywhere the lattice is intact, the lattice is doing the work. And one less obvious step worth considering. Pair SNOM with high-resolution AFM or SEM topography. The topography has its own Fourier spectrum, its roughness, its grain structure, its imperfections. Compare that spatial spectrum to the wave vectors of the near-field modes you measure. If they line up, your unexpected resonance may actually be enabled by specific nanoscale roughness components. That's not a defect, that's a design parameter you didn't realize you had.
Momentum mismatch isn't a quirk of nanophotonics, it's the engine of it. Every grating, every prism, every nanostructure exists to bridge the gap between the light you have and the modes you want. And once you accept that there are many modes, not just SPPs, but a zoo of resonances that all look alike in the far field, SNOM stops being a niche instrument and becomes a basic tool of identification. The near field is where the truth lives. If you take one thing away, don't trust a reflectance step. Trust the field map.